All right, let's get started. So first, a few class logistical notes. So today is actually going to be the last lecture that I'm going to give in the class. And it will be kind of a mixture of a research lecture about a topic of my choice, which I'll mention to you shortly, unless you read the title, in which case you already know what it is. As well as kind of half the lecture that will be spent on challenges, open problems, and just generally sort of some philosophical musings on what to think about for the future. But of course, this isn't the last lecture of the course. We still have 4 more lectures to go. So on Wednesday this week, we'll have a guest lecture by Ophir, who will be coming here from Google Research, and he'll tell us about some interesting stuff related to off-policy estimation and convex conjugates. So there'll be kind of a cool, kind of more theoretical lecture. Next week, we'll have a guest lecture by Chelsea Finn from Stanford, who will talk about probably some topics related to meta learning. And then the last week of class, we'll have 2 guest lectures, one by Carol Hausman from Google Robotics, talking about multitask learning and things of that nature, and one by Karen Liu from Stanford University, talking about computer graphics. So I think all 4 of these guest lectures will be wonderful, and I very strongly encourage you, if you're watching me on YouTube right now at home, to make the effort for these guest lectures to come out to class in person, ask questions of the speaker, and generally kind of get the full CS285 experience. That's good for the speaker because then they're not talking to an empty room, and it's good for you because you get to interact with them a little bit. So do come to class for the next 4 lectures. And then for today's lecture, enjoy watching me from home in your pajamas, except for those of you that are in class today who will also get the full 285 experience. So yeah, please attend the guest lectures. It's nice for the speaker, and it's also nice for you. Today's lecture. So today, usually what I like to do for the last lecture that I give in this class, I like to select some topics that are a little more kind of research focused, and that's what I did for this lecture. It's actually a topic that I haven't spoken on before, but we'll see how it goes. It's something that I think is pretty interesting. So today I'm going to talk about information theoretic exploration. And this discussion will be about this somewhat peculiar problem where we take a little departure from the standard reinforcement learning problem statement. So usually in reinforcement learning, we assume that someone gives us an objective. And when we talk about things like exploration, we're really talking about exploration in service to that objective. So even though in order to play something like Montezuma's Revenge, you need to get your agent to do all sorts of different things, visit novel states and so on, it's all in service to doing well at that game. But you could also imagine a more open-ended sort of exploration where you're not given an objective at all, and you're asked to do things in the environment that might prepare you for other tasks later down the line. And we'll try to make this a little bit more concrete and then discuss some algorithms inspired by ideas from information theory that allow us to instantiate this in practice. And this is very much going to be kind of a research-focused talk, so there isn't sort of a single known method for solving this problem, and there's just a collection of papers. And of course, the discussion in today's lecture will be unabashedly biased in favor of the papers that I know more about, but hopefully it'll at least give you a taste for what's going on in this area. And then part 2, after the break, we'll talk about, we'll switch gears a little bit, and we'll talk about challenges and open problems in deep RL. So this will really be meant more to kind of give you a little bit of food for thought for your final projects, discuss things that are currently difficult, things that we don't have good solutions to, and a few thoughts about how we might go about trying to find better solutions to these problems. So the goals for today will be to provide a high-level overview of information theoretic exploration and unsupervised reinforcement learning, so that's part 1. Talk a little bit about trade-offs and trends in current deep RL algorithms in part 2, and provide some perspective on current open problems and challenges. All right, so let's start with part 1. So the discussion in this part of the lecture will really deal with this question. What if we want to recover diverse behavior in some kind of MDP, only without the reward, where you're not actually told what the goal is? So this is something that might at first seem a little peculiar given all the discussion we've had in this class about maximizing rewards, but it's not that peculiar if you consider what an intelligent creature, an intelligent organism needs to deal with in reality. So if you're a child and you're playing with toys and so on, you might not have a very particular task-oriented goal in mind. You might, maybe at first you could think, well, maybe children have some sort of incentive. Maybe they want to get food, they want to get whatever, but they really don't. They're just kind of playing around with things. If you observe children playing, they don't take random actions. They don't execute a maximum entropy suboptimal policy. They do things that are coherent, but not informed by a very specific task goal. In fact, arguably, they invent their own task goals. So why might we care about agents being able to do these sorts of things? Well, if we learn skills without any supervision, if we learn sort of a battery of skills, a repertoire of skills, we could imagine then using them to accomplish downstream goals. So if in the process of playing around with objects in their environment, our agents discover, for example, how to assemble towers out of blocks, then when someone comes along and says, okay, today your job is going to be to build 50 towers for me, well, something that they did during this play phase will have prepared them to solve that problem very efficiently. You can learn sub-skills that you can use with hierarchical reinforcement learning. So if you sort of figure out the suite of coherent behaviors you can execute in the world, then you could imagine learning a more goal-directed higher-level policy that sequences those skills to perform much more complex and temporally extended tasks. And you can explore the space of possible behaviors. You can essentially build up your knowledge of the world so that when you're then presented with a difficult exploration task, something about that knowledge that you've built up during your play phase might prepare you to tackle that difficult exploration task much more efficiently. So this is all a little bit vague at this stage, but we'll see some more concrete examples of some of these things in action later on. Let's go through kind of an example scenario to try to maybe make this a little more specific. Let's say that you have a rather messy kitchen, and you purchase, the household robot version 1.0, and this household robot is placed into your kitchen, and it's just told, well, today I'm going to go to work, household robot, interact with my kitchen, figure out what it is that you can do there that might be useful, and when I come home in the evening, I'm going to give you an actual task to do. So the robot now knows that it has, whatever, 7-8 hours to mess around in this kitchen and figure out all it needs to know about this kitchen. That's its unsupervised training time, so that at test time, it can be prepared for some unknown future goal. So then when you come home in the evening, you might say, okay, well, tonight I really need the dishes done because I'd like to eat dinner and all my dishes are dirty. So the task I'm going to give to my robot is to clean the dishes. It didn't know this during the unsupervised training phase, but if it had the right sort of exploration algorithm, maybe during that unsupervised training phase, it might have figured out some behaviors or skills that would have prepared it to master this dish cleaning task very efficiently when it's actually given the task goal. Okay, so that's sort of an example setup to kind of get you thinking about the sorts of challenges we might face. So in this lecture, what I'm going to discuss first are some definitions and concepts from information theory that might help us to think about these sorts of problems. And then I'll talk about learning without a reward function by reaching goals. So this will be a very specific set of tasks that involve reaching particular desired states. And then I'll talk about how it can go beyond reaching specific states and into unsupervised acquisition of skills, which are much more open-ended. And then I'll conclude with a little bit of a discussion actually tying some of these ideas to some of the discussion of meta-learning that you heard about in Kate's lecture last week. All right, so let's start with some definitions and concepts. There's a question?
Yeah, why isn't this problem sort of solved by model-based reinforcement learning, and then you can use there's that paper, can you use model-free reinforcement learning after model-based reinforcement learning?
Right, so the question is, well, can we use model-based reinforcement learning to tackle this sort of problem? The answer is you absolutely could. So one very reasonable interpretation of what's going on in this video, I'm going to show it again because it's a good video, is that maybe in the process of interacting with the world in these unstructured ways, you're acquiring some understanding of physics, essentially. You're figuring out the relationship between causes and effects, and knowing that relationship will then allow you to solve new tasks, as we talked about in the model-based RL lectures. One of the nice things about model-based RL is that you can repurpose your model to new tasks. That's definitely a possibility. A lot of the ideas I'll actually discuss in today's lecture are somewhat orthogonal to that, because beyond whether or not you train models, you have to actually decide how to collect the data that's going to give you the right kind of experience. So all the methods I'll talk about are actually model-free methods, but many of them can be adapted to model-based methods. And you actually face the same problem. You face the problem deciding what to do to collect the right kind of data. Any other questions? Okay. So let's start with some definitions and concepts from information theory, partly as a math warm-up, and partly to give us a taste for how some of these concepts might be utilized for unsupervised RL. So we'll start with, with the very basic stuff that you guys are probably all already familiar with. First, distributions. Hopefully we all know what a distribution is. but I promise it's going to get a little more sophisticated shortly. So if you have some points x, so those are your points x, you have a distribution p of x that tells you what the density of those points is. It's the most basic concept. But then when you have a distribution, one quantity, one information theoretic quantity you can use to understand what's going on with that distribution is something called the entropy. We sometimes write entropy with a script h. And the entropy is formally defined as the negative expectation of the log probability, which might seem a little bit cryptic, but all that's really saying is it's quantifying how broad your distribution is. So the intuition for why it's doing that is that if your distribution is really, really peaked, then you'll have a large log probability. So if you take an expectation of a large log probability, you'll get a large number. If you take the negative of a large number, you get a very small number, a very negative number. If your distribution is very, very broad, then most of your log probabilities are small, which means that the expectation of those small numbers is small. So then when you take the negative of that, you get a larger number. So intuitively, the entropy sort of captures how broad this distribution is. The more of the space of possible values of x are covered, the larger the entropy. And this is going to be important because when we talk about unsupervised reinforcement learning, we'll want exploration strategies that cover broad distributions on the state space. OK. Now, the next and the last identity, which is the most important, is mutual information. And we're going to actually use a particular definition of mutual information that is expressed in terms of entropies, but I'll first define it sort of in the textbook way. So mutual information is a quantity that captures intuitively how dependent two variables are. So it's a function of two variables, x and y. Formally, it's defined as the divergence between the joint distribution over x and y and the product of their marginals. Now, what does this mean? Well, for those of you that recall the definition of independence, two variables are independent if the product of their marginals is equal to their joint. So if p of x comma y is equal to p of x times p of y, then x and y are independent of each other. That also means that their divergence is 0, which means that their mutual information is 0. So if two variables have nothing to do with each other, they have 0 mutual information. That makes total sense. If two variables are very strongly dependent, they have a very close relationship, then the scale divergence will be large, which means that their mutual information will be large. For those of you that don't remember the definition of scale divergence, it's the expectation under the first argument of the log of the ratio of the two arguments. I don't think this equation really intuitively communicates very well what's going on, so let's try to communicate it in pictures. So there's two variables, x and y, and these green dots are showing samples from the joint, from p of x comma y. So here are two different joint distributions, this one and this one. All right, so as a quick quiz, which one of these has a higher mutual information? Raise your hand if you think the top one has higher mutual information between x and y. Now raise your hand if you think the bottom one has higher mutual information. OK, good. Right, so it's exactly what you expect. High mutual information means that x and y are strongly dependent. Low mutual information means that they are closer to being independent. OK, that's kind of fairly straightforward stuff. So one of the things that kind of helps to think about mutual information in the context of the sorts of reinforcement learning problems that I'll discuss is a particular way of writing mutual information in terms of entropies. It turns out that you can equivalently write mutual information as the difference between two entropies. The entropy of the marginal p of y minus the entropy of the conditional p of y given x. Now intuitively, why does this make sense? Well, it makes sense because if x and y are very strongly related to each other, like they are in this top picture, then you should be able to predict y very accurately from x. So in this picture, this is basically the line y equals x plus a little bit of noise. So if y is almost equal to x, that means that the conditional entropy of p of y given x should be very, very low, meaning that if you know x, you can predict y very accurately. However, it's not enough for this thing to be low. You also need the first entropy to be high. That intuitively just says y tends to vary a lot. So if y tends to vary a lot, but it's easy to predict from x, then the mutual information between x and y is very large. If y doesn't vary a lot, it kind of doesn't matter that it's easy to predict from x because it's easy to predict even without knowing x. So if y was always equal to like 0.5, yes, this conditional entropy would be very low, but so would this one. That doesn't mean that y is predictable from x, it just means that y is predictable, period. If y is very hard to predict, but very easy to predict once you know x, then the mutual information is large. And this intuition is going to come up again and again when we talk about mutual information in unsupervised RL. Does anybody have any questions about this? Okay, so it's pretty straightforward stuff so far, hopefully. So how does this show up in RL? Well, you can have a distribution over states. So one very common distribution that we'll deal with is pi of s, which is the state marginal distribution of a policy pi. It's the distribution over states that a policy visits. If you want a policy that explores very well, that covers the space effectively, then you might want a very high entropy for that state marginal. So if the entropy of pi of s is large, intuitively that means that your policy visits a wide range of states, which probably means that it's going to discover lots of interesting phenomena in the world, it's going to play with all the toys, and find all the interesting situations. So in some sense, you can imagine that the entropy of pi of s quantifies the coverage over the state space. Here's an example. This is just an example of mutual information in reinforcement learning. I'm not actually going to talk about this in great detail, but I just want to use it as an example because it sort of grounds that definition of mutual information from the previous slide very nicely in a reinforcement learning setting. So what I'm going to write down next is something called empowerment, which is an information theoretic quantity in RL. This is kind of popularized by Daniel Polanyi. And intuitively, empowerment captures the capability of the agent to affect the world. And the way that it's defined is as the mutual information between the next state and the current action. There are a bunch of variants on this. Sometimes it's defined as next state and current action given current state, but I'll just use this simple definition for now. And going back to the equation from the last slide, I can write down the mutual information between st plus 1 and AT as a difference of two entropies. The first entropy is the entropy of st plus 1, and then the other one is st plus 1 given AT. So the mutual information between st plus 1 and AT is large if your agent visits a very wide range of states, that's captured by this first term, and the action that it takes very, very strongly predicts the next state that it will visit. Now, this doesn't always have to be the case. You could, for example, have an agent that really likes playing the lottery. Now, if it really likes playing the lottery, then the next state is quite random and is maybe not so affected by its actions. So it might have a very large state coverage. It might visit many different states, but its next states are not predicted by its actions. So that would have low empowerment. If you have an agent that tries to put itself into situations where it has a great deal of control over the world, then it might have a very low value for this second entropy, and that would be high empowerment. So basically, intuitively, it means do your actions very strongly influence the world, ideally in fairly deterministic ways. And from there, you might kind of figure out why this is called empowerment, because it reflects, in some sense, the control authority that the agent has over the world in a kind of information theoretic way. So we're not going to go into great detail about this. This is really meant more to serve as an example of how, by taking some of these information theoretic definitions into the world of RL, we can get quantities that reflect interesting properties of how the agent interacts with its environment. Okay. So with these definitions, we can talk about the first kind of technical portion of this talk, which is learning without a reward function by reaching goals. And this will be sort of a somewhat specific notion of unsupervised RL, which we'll then generalize in the next portion to talk about executing general skills rather than just goals. So let's come back to our example scenario. We have our robot. At training time, it's not given any objective, and it needs to prepare for an unknown future goal. So if we approach this problem pragmatically, maybe one of the things that we need to think about is before we even imagine how we're going to explore this environment, we need that robot to somehow receive objectives from its user at test time. So when I come home and I want to tell the robot to do the dishes, I need to have some way to communicate that to the robot. So let's nail down a somewhat arbitrary but very convenient interface, which is that we're going to specify objectives to our agent by telling it the state that we would like it to reach. So maybe right now, the state is that the dishes are in a messy pile on the table. I'm going to provide the agent with an example state that I would like it to reach, which is that the dishes are nicely laid out in a nice table setting, and its job is to make this state equal to this state by manipulating the world. It's not the only way to specify objectives, but it just happens to be a very convenient one. And now, of course, having nailed down this interface, now we need some way for the agent to perform that unsupervised practice phase. So what we're going to do is we're going to have the agent build an internal model, a generative model, of states that are valid states. There are a variety of different generative models you could use for this. The particular one that's going to be used in the prototype that I'm going to discuss is something called a variational autoencoder. But the same exact thing could be done with other generative models. So you could, if you have a very simple low-dimensional state space, you could just have a tabular representation of your generative model. If you have something really complicated, you could use a GAN. I'm going to discuss this in terms of VAEs. First, because all of you hopefully know about VAEs if you watched the supplementary variational inference lecture. And second, because this keeps the math quite manageable. So if you can build a generative model, basically a model that, from which you can sample valid states, then a very reasonable way to perform that unsupervised exploration is to simply sample states randomly from your generative model, pretend as though they were the goal, and then train your policy to reach them. That's a very simple way to explore the space, and as long as you can train a generative model, you can do this. But this has a pretty severe problem. Does anybody have any idea about what problem you might get if you try to do this? Yeah.
Just box to reward, like the reward in this.
Right. So one problem is that the resulting reinforcement learning problem might be kind of tough because you're essentially rewarding your agent for reaching the goal that it hallucinated, and if it doesn't reach it, then it doesn't get a reward. And that's absolutely true. In fact, from a reinforcement learning standpoint, these goal-reaching tasks tend to be a little bit difficult. We're not going to talk about that challenge too much because we want to focus on the exploration part, but there's definitely some open problems there. Yep.
What if it's like long horizon and it takes a lot of actions to get to
So it might take a really long time to reach the goal, so you might also have a very difficult learning problem in that sense. But maybe there's a more fundamental issue with the goals themselves, right? If you're using a generative model to propose goals, where did you get that generative model? Well, you presumably trained that generative model on the data that you've seen. So initially, my generative model is not very good. It proposes some arbitrary nonsense. I go and explore the world largely randomly. I get a little bit of data in the neighborhood around my starting state, and then I propose more goals that look like those starting states. So the trouble with this is that you're not really diversifying your range of capabilities. You do some things randomly, and then you propose more things that look like those things that you did randomly. So it's kind of the recipe to just keep going in circles and keep trying the same thing over and over again. In order for this thing to do something interesting, and more importantly, in order for us to be able to write down an objective that describes what it's doing, we need to be able to somehow get it to cover the space efficiently, to actually diversify the range of states that it's trying to visit. So intuitively, what we can imagine doing, let's say that we have, well, let me just go through the outline of the method first, and then I'll tell you how to fix this problem. So to outline the method in somewhat more formal terms, let's say that for our variational autoencoder, p theta of x given z is our decoder. So theta are the parameters of the decoder. We have our prior p of z, and we have our encoder q phi of z given y. So this is exactly the same as in the variational inference lecture from before. We're going to have step one, which is to propose a goal. You propose a goal by sampling from your model. The way that you sample from a VAE is, of course, ancestral sampling. So you sample your goal latent state from your prior, and you sample your goal state from the decoder. So you get a goal xg. Then you attempt to reach the goal using your policy. And your policy is now, of course, parameterized by your state and also the goal. So you have a different policy for every goal. So this can be instantiated by a neural net that takes in the state and the goal as input. And you might not reach your goal perfectly, so in general, we'll just say that you reach some other state that we're going to call x bar. If your policy is very good, then x bar will be very close to xg, but in general, it might be a little bit different. And then you're going to use the data that you gathered from this attempt to update your policy pi. And then you'll also use that data to update your generative model. And of course, the generative model consists of the encoder and the decoder, so you're going to really update theta and phi. And of course, this is a sort of a very rough pseudocode description of this. In reality, you would use like a replay buffer. So when you attempt the task, you would add x bar to your buffer, and then you would update your policy and your generative model using all the data in your buffer. But I'll just write it out in this sort of online way just to keep the notation simple. And then, of course, you keep going. So now, as we mentioned, there are a few problems with this. One is, of course, attempting to reach the goal might be difficult due to sparse rewards and long horizons and so on. So we need very good RL algorithms for this. But then the other maybe more fundamental problem is that if you use the data to update p theta and q phi naively via maximum likelihood training using the variational lower bound, then you'll just keep proposing the same kinds of goals that you've seen before. So we need some way to diversify. Intuitively, the way that we can do this is we can say, well, let's say that these circles represent the states that you visited. Just from looking at this, you can kind of tell that some of these states out on the periphery are, they're a little bit more novel than the ones here in the starting region. So you might say, well, if given the choice, you would rather practice these goals out on the periphery more because those seem to be the more interesting goals, rather than the ones here close to the start because those are the ones that you're already probably doing a pretty good job of visiting because there's so many of them there. So you'd like to somehow modify or skew the distribution over goals before you fit your generative model to upweight these more interesting goals that are out on the periphery. And if this is starting to sound a lot like the exploration lectures, it's because it is actually very closely related. So if you could somehow find these rare goals and upweight them, then when you fit your generative model, it'll assign a bit more mass to those tails so that when you sample the goals again, you'll get more goals out on the tails, you'll explore those tails a little bit more, and then just through random noise, you'll sort of push the boundaries a little bit. And then you'll get states visited even further out, you skew the distribution again, refit, and then you get states even further out. So that's sort of what we'd like to see. Let's talk about how we can instantiate that. So the key is going to be in step 4. So in step 4, when we update our generative model, we'd like that generative model to emphasize the states that are a little bit more novel, a little bit more unusual. So this is the step that we'd like to modify. And of course, the new experience that we're getting when we do step 4 is this x bar that we reached. So we'd like to basically make a decision about how we're going to train on x bar in order to give novel x bars higher weight. So that's this step, the skew step. So a standard maximum likelihood estimator would essentially train theta and phi to give you the argmax of the expected value of log px bar, expectation taken under all possible x bars that you could reach. And of course, if you have a VAE, then you would approximate this quantity by using the variational lower bound. So in a VAE, p of x bar is of course intractable, so instead you use the expected value under q and so on, the variational lower bound. So what we're going to do instead is we're going to have a weighted maximum likelihood estimator where we're going to put some weight on x bar, and we're going to try to choose that weight so that we upweight the tails. And the interesting result here is that if you choose wx bar to be the probability of x bar under your previous generative model raised to the power alpha, where alpha is any number between -1 and 0, so that means that your weight is, it can equivalently be written as 1 over p theta of x bar raised to the power beta, where beta is between 0 and 1. So essentially, states with higher probabilities end up getting lower weights. Then you can actually show that for any value between -1 and 0, the entropy of your generative model will increase. Now, how much it increases, of course, depends on what you actually choose for that coefficient. You might, at this point, see that there's sort of a special case of this. If you reach the goal perfectly every time, meaning that x bar is equal to xg, and you choose alpha to be -1, this is actually just importance sampling. Because if you weight by 1 over p of x, then you're importance sampling your distribution into the uniform distribution, and the uniform distribution is the highest entropy distribution that you can get. But of course, this by itself is not possible for two reasons. One is that you don't actually reach x bar, you reach some other state. You don't actually reach xg, you reach some other state x bar. And second, if you actually weight by 1 over p theta of x, you might have very high variance importance weights. So that's why I use a little exponent. But the interesting result is that for any exponent between -1 and 0, if you repeat this process over and over again, you will increase the entropy every time. And of course, if you increase the entropy every time, then eventually the only thing you can converge to is the uniform distribution. It might just take you more than one iteration. So if you reach the goal perfectly and you weight by 1 over p of x, then you will, in the infinite sample limit, get to the uniform distribution in a single iteration. But in practice, that usually doesn't work. So you use a slightly gentler exponent and also allow yourself to not reach the goal perfectly. So that's kind of interesting. Now we have a way to increase the entropy of our goal distribution. And of course, since we're always training it on real states, it'll only give non-zero probability, if it works properly, to real states. So fake states, states that are unreachable, will not get any probability. So you'll get the uniform distribution over valid states. So now the next question we could ask is, does this thing actually optimize some well-defined objective? But before we get to that question, do you guys have any questions? Yeah.
When fitting the MLE, is it using all the data from the past or long?
Right. So the question is, when you're doing step 4, when you're fitting the model, are you using all the data from the past or just the data that you just collected? So in the actual implementation of this algorithm, the thing that has actually been tested, use all the data from the past. In theory, if you collect enough data in step 2, it kind of doesn't matter. But in practice, of course, you want to be data efficient, so you would reuse all your past data. Any other question? OK. Yes?
So you say that we would only have like a distribution over valid states, but we're training a fitted model, right? So like it's like a distribution. So like it's like smooth distribution. It could still.
Yeah, so the question was, well, I just said that you get a distribution that gives non-zero probability to valid states, but you have a function approximator, so is that really true? So the answer is, if your function approximator does its job properly, meaning that it doesn't underfit and doesn't overfit, then you will get a distribution over only valid states. But of course, as with any function approximator, it can make mistakes and assign probability to invalid states. The reason this is relevant is that what you actually want in the end, and we'll discuss why you want this, is a distribution that has the highest possible entropy over the set of states that are valid. Because proposing goals that are invalid states, like for example, if your goals are images and you just make up some image that doesn't actually exist in your Atari game, that's no good. That doesn't help anybody. So you want the highest entropy, but only for things that are legit. The reason that you might reasonably expect to get that is because you only ever train this model on states that are actually visited. So presumably, if you visited that state, it's a real state. But of course, your function approximator can definitely make mistakes. Any other questions? Yeah?
And also, why do we condition our policy on X and X shaped or like images? Like, wouldn't it make more sense to condition them on like the latent space?
Right. So the question is, for this policy, pi a given x comma xg, wouldn't it make more sense to condition on maybe like the latent state z? You can absolutely do that. So this is sort of written out in the most general way, but you can definitely reuse the same VAE model to give you a better state representation or goal representation for the policy. And in fact, the practical implementation of this algorithm does exactly that. But in general, you don't have to. OK. So now, the interesting thing that I want to discuss a little bit is what objective this whole procedure corresponds to. So we've made this choice where we instantiate this skewing step by weighting our data according to p theta x bar raised to the power alpha, where alpha is some number between -1 and 0, which intuitively just downweights states that had high probability under your previous generative model and upweights states that had low probability under your generative model, which should do exactly what this picture is showing. So what is the objective? Well, if you're increasing the entropy, and by the way, the discussion that's about to follow is a little bit informal. It's made more formal in the paper, but I just sort of want to make sure to give you guys the intuition. If what you're doing is you're increasing the entropy of your goal distribution every step, then eventually you're going to have the goal distribution with the highest entropy. So that means that you're somehow maximizing the entropy of P of G, where G is your goal. But that's not all that you're doing. You're not just training a generative model, you're also training a policy. So goals get higher entropy due to this skewing procedure. But what does RL do? Well, RL is trying to reach the goals. So your policy, pi of a given s comma g, is trying to reach the goal g. If your policy does a very, very good job of reaching the goal, then the last state is going to be very similar to the goal. So as pi gets better, the final state s gets closer and closer to g. And what that means is that p of g given s, the probability of a goal given the last state, becomes more and more deterministic, right? Because if your policy is really good, it always reaches g, that means it's really easy to predict g by looking at the last state it reached, because you say, oh, it's a good policy. Whatever it reached was probably the goal. So p of g given s becomes more and more deterministic, which means that its entropy should decrease if RL is working well. So now we have something kind of interesting. We're increasing the entropy of P of G, and we're decreasing the entropy of P of G given S, because that's what RL is trying to do. So that's our goal, and that's our final state. So that means that we can write our objective as maximizing entropy of P of G minus entropy of P of G given S. So RL is taking care of the second term. The generative model fitting is taking care of that first term. This is made a little bit more formal in the paper. So that's kind of cool. If that's our objective, that means our objective is really the mutual information between the state and the goal. So that means that you can cover the space well, get close to the uniform distribution over goals, and get a good goal-reaching policy, meaning a policy that will deterministically reach the goal that you command, simply by maximizing the mutual information between the final state and the goal. And in fact, this idea is going to come up again and again in some of the methods that I'm going to discuss, that a pretty decent objective for unsupervised reinforcement learning is the mutual information between the states that you visit and the command that you give to your policy. So in this case, S is the state you visit, and G is the commanded goal. So this leads to good exploration, because you're maximizing the entropy over the states that you visit, and effective goal reaching, because you're minimizing the entropy of the goal given the state that you reached. OK, so cute little robot video. If you actually code this up with a few delicate design decisions, you can actually get a robot to do fun things like propose image goals to itself, to play around with a little door, and then actually learn to open that door without any supervision. So here the robot was placed in front of the door and allowed to operate for 25 hours without anybody telling it what it was supposed to do. And it figured out pretty quickly that, yes, it can move its arm around, it can wiggle its hand a little bit, but the really interesting thing to do in this environment is to play around with the door. And after 25 hours, it gets pretty good at opening and closing the door. All right. So let's now briefly discuss the next topic, which is going beyond just reaching goal states. So next, I'm going to kind of generalize this idea. We're still going to have a mutual information objective, but we're now going to use that mutual information objective not just to reach diverse goals, but to actually execute diverse skills. So what we want is we'd like a policy that takes actions conditioned on a state and some kind of skill index z. So z is no longer going to have the semantic meaning of a goal state. It's just going to be an arbitrary latent variable. So it could be a categorical variable that takes on 1,000 different values. So you can think of it as a task index. And what we would like is for different task indices to have the policy do different things. So maybe this is like a little 2D navigation environment. Our 0th skill does something like this thing shown in green. Our skill number 1 does something like that. Our skill number 2 does something like the blue lines, and so on. So if you give it different skill indices, it should do different things. Now, you might imagine that maybe we can use something like the maxent_RL that we discussed in an earlier lecture, or this goal-reaching business that we discussed just now to get this. But there are a few reasons why these things don't quite get us what I described in that picture. So if you do the maxent_RL from before, that's no good because it's maximizing action entropy. It's not trying to maximize the distribution over skills. You can imagine doing the goal-reaching from before, but reaching diverse goals is not the same as performing diverse tasks. And this is a little bit subtle. So not all behaviors can actually be captured by goal reaching, and I'll give you just one example. Let's say that you'd like to go to this green circle while avoiding the red circle. There's actually no goal reaching behavior, no behavior where you can specify a single goal and get to that goal as quickly as possible that'll give you this kind of thing. So it's not enough to just reach goals. And of course, you want policies that are actually controllable. So if you just do kind of the maxent_RL thing from before, you might get diverse behaviors, but you might not get the ability to specify different task indices to actually control what they do. So the intuition for the method that I'm going to describe that actually does this is that different skills should visit different state space regions. Not necessarily just different goals, but different regions over the course of the entire skill. So if you want a skill like this, like in this picture, maybe you want your state space region to be things that are close to the green circle but far from the red circle. So here's how we can do it. for any kind of RL problem, we're going to have our policy optimized with respect to some reward function. So really the only choice that we're going to need to make is how do we construct the reward function. So in this case, since we have different skill z, we'll have a different reward function r for every z. And then we have to choose the form of r. And the choice that we're going to make is we're going to reward states that are unlikely for other z's. So the reward s comma z is going to be large for any s that is very rarely visited for other z's. And the way that we can do this is by representing the reward function as a classifier. So the reward r will be a classifier that tries to classify which z the policy was commanded to execute based on the state. So it's like a game. I'm going to pick a z. Maybe I'm going to say, today you're going to do z equals 1. And the classifier looks at the states that the policy visits and tries to guess which z did I command. So you have this interaction between the environment and the agent. The agent gets a skill index z, which we can think of as just an integer. And then this discriminator, this classifier, looks at the state and tries to guess what z did I command. And the reason that this will lead to the emergence of distinct skills, you can kind of get that intuition from this visualization. Let's say that I have just two skills, a green skill and a blue skill. And initially, the policy just does random stuff. So maybe the green skill and the blue skill result in very similar behavior. So now the classifier is going to go in and is going to do its best to draw a boundary between green and blue. So maybe it'll draw this boundary, right? So green and blue are pretty similar, but maybe there's like a little bit more blue over here and a little bit more green over here. So now the policy gets to go. And the policy is cooperating with that classifier. It's trying to visit states in such a way that the classifier will not make mistakes. So the classifier thinks that this lower half is blue, this upper half is green. So the policy will try to separate these out to let the classifier be more accurate. And then the classifier gets to go again. It gets to draw a better boundary. So now it looks at this as like, oh, I can kind of separate these. Let's draw the boundary like that. Then the policy gets to go again. It'll separate them even more. Then the classifier gets to go, and so on. Now, of course, in this example where there are only two skills, the solution is maybe not very satisfying. You'll just have one skill that does random useless stuff in the top half, another skill that does random useless stuff in the bottom half. But as you increase the number of skills, as you increase the number of boundaries that you draw, eventually these skills have to specialize more and more, and then they'll actually start doing more useful things. So if you actually do this with a larger number of skills, tens of skills, and you run this on some of the environments that you guys had in your homework, some of the Mujoko environments, then you get some fun skills like this. So if you do this on half cheetah, the half cheetah decides that one of the skills should run forward and another one should run backward. It's very easy to tell a forward run from a backward run. And then for some reason it decides that another skill should do this kind of really cool flip because the really cool flip looks very different from running forward or backward. Now there are other skills too. Some of them do boring stuff. Some of them it just kind of face plants and sits on its face because that's also very easy to distinguish from running forward and backward. But it does a variety of different things, and these things are dynamically kind of somewhat elaborate. Here's the same thing with the ant. So the ant kind of wiggles and runs in different directions. And here's a kind of a canonical little toy task called a mountain car. For the mountain car, actually, some of the skills that are learned just outright solve the task. So if you look at this top one, it actually figures out that getting to the top of the mountain is one of the things it can do. That's easy to distinguish from all the other things it could do. OK. Any questions about this? Yeah.
So for a lot of these more like unsupervised like frameworks, does it become a lot more like susceptible to randomness and like random seeds? Because now like with regular RL, it's already like randomness has a big effect, but now this seems like it would be
right. So the question is, I'm going to rephrase your question a little more provocatively. So this deep RL stuff is kind of a mess. You run it 5 times and you get 5 different answers. And now we're making it even more random by letting it have this sort of arbitrary bootstrapping off of itself. The answer is, yeah, it gets way more random. And you run this like 10 times and you get 10 totally different sets of skills. Part of the intuition for what's going on here, it's very much like what you get when you do expectation maximization. So if you do EM clustering on data that is not very cleanly decomposed into very obvious clusters, you'll get different answers when you run at different times. The same thing happens here. OK. Now, one of the things I mentioned as a potential application of these ideas is for hierarchical RL. And you can actually do that pretty well. So you could, for example, use some of the skills that are learned via this unsupervised procedure as primitives for hierarchical RL. So there are two tasks that are being tested here. One is this cheetah hurdle, where the cheetah needs to run and jump over some barriers. And the other one is kind of a waypoint navigation task for the ant. And in all these cases, you get some benefit from doing this unsupervised skill pre-training, shown in red here. The purple one uses unsupervised skill pre-training, but where the states that the classifier gets to look at are restricted to XY positions. So that's a way to inject a little bit more like kind of prior knowledge into this. So you can use these things for hierarchical RL. Now, that was kind of the practical instantiation, but I wanted to connect it back to the theory and to show you that, in fact, what this algorithm is doing is not all that different from what we discussed before with goal reaching. So as a reminder, our policy is maximizing expected reward, and our expected reward is a classifier. It turns out that this actually also corresponds to maximizing mutual information, but now it's the mutual information between Z and S. So before we had mutual information between G and S, meaning high mutual information between the goal that you commanded and the state that you reached. Now it's high mutual information between the skill index that you commanded and the state that you reached. So a very similar principle. Why is that true? Well, because the mutual information is the entropy of the Z minus the entropy of the Z given S. The entropy of the Z, that's just our prior. So the way that we make the entropy of Z large is just by commanding random skills. So long as you sample your skills, the Z's, uniformly at random during training, you're making this H of Z as large as it could possibly be. The second term, Z given S, that's exactly what our classifier is doing. So if our classifier accurately classifies the Z given the state, then we're minimizing the second entropy. So that means that taken together, this method maximizes the mutual information between Z and S, which looks very, very similar to what we had before, except now, instead of grounding our commands specifically in goal states, our commands are these latent codes. All right, now to conclude this portion of the lecture, I just want to discuss another way that we can use these unsupervised skill learning methods to connect it up to the meta-learning stuff that Kate discussed last week. So first, as a brief aside, I'm going to tell you about a little problem with meta-learning, which I think Kate didn't mention. Something called meta-overfitting. So as all of you probably realized from the discussion last week, meta-learning requires a task distribution. And we specify that task distribution typically by hand. So if you, for example, manually define a bunch of tasks for the ant to run in different directions, and you use that for meta-learning, then you will get an efficient learning procedure that can then quickly adapt, maybe use mammal, it can quickly adapt to running in a single direction using a very small amount of data, maybe just like one gradient step or something. But you have to design these tasks in order to get this to happen. And if you design those tasks poorly, maybe you have too few tasks, then you're not going to get this behavior. Instead, you're going to get your meta-learning algorithm to just memorize the training tasks and only be able to regurgitate those things that it was actually meta-trained on and not generalize to new tasks. So when there are too few meta-training tasks, you can meta-overfit. And that means that specifying task distributions is quite hard, especially for meta-RL, because you have to actually design these reward functions for everything. So what if we could propose tasks automatically? What if we take some of those ideas from the unsupervised skill learning and connect them up to meta-learning to basically use those unsupervised skill learning procedures as an engine to propose fake tasks for our meta-learning algorithm to practice? So you could imagine sort of a pipeline for unsupervised meta-RL where you have unsupervised task acquisition to propose tasks that meta-RL then practices, and then at test time, maybe a person gives a real reward function to your model, and it can adapt quickly to that real reward function. So tasks, in this case, can just be defined as different reward functions. Just like we had before, it's going to be an R, S, comma, Z, where Z is the index of the task. And we just need to produce very diverse R of S, comma, Zs. And then your meta-RL algorithm is basically doing the adaptation. So it's finding a model pi that, in expectation over all your tasks, gets the largest reward after adapting to that task. So that's kind of the standard meta-learning paradigm from before. So then you could imagine proposing tasks according to that mutual information objective. So basically propose tasks such that Z has high mutual information with S, maybe using exactly the procedure from before, and you'll be able to generate these synthetic tasks and get meta-learning to actually learn something even without people telling it what tasks to practice. So that's kind of a reasonable idea. It's described in this paper called Unsupervised Meta Learning for RL. And it kind of more or less works. The difference from before is that the result is not a policy that's conditioned on Z. So in the skill proposals before, you end up with a pi of A given S comma Z. Here, that's not the result. The result here is actually a model that can learn quickly from reward. So the final model you get from meta learning is not conditioned on Z. It's actually a model that can use experience with rewards to figure out how to solve a new task, which is actually a pretty significant difference. Short version is that it mostly works. It works better than learning from scratch, at least. It's a little hard to figure out what else to compare it to. And you can kind of propose decent tasks this way. OK, so that's the information theoretic exploration and unsupervised reinforcement learning. At this point, if anybody has any questions, I'd be happy to take some questions. And then we can take a little break. So any questions? OK, so let's take a short break. We'll be back at 11:05. And then we'll have some concluding remarks and open problems. So see you all in 3 minutes. Hello.
Yeah, I just have questions.
Mm-hmm.
I was really excited when you brought up empowerment because
Okay.
I recently started a project involving how to use empowerment for human collaboration and
Mm-hmm.
coordination. And I was wondering if you knew if anyone like in your group or else otherwise at Berkeley working on using empowerment.
Mm-hmm. Well, so empowerment, it ends up being just mutual information between actions of future states. So people have actually used those kinds of objectives for learning exploration policies, for learning representations. You can imagine the same thing as a state representation objective, for learning prediction and so on. Yeah, there are people working on variants of this, not just for exploration, but also for things like representation learning. So if you'd like to get some pointers, maybe send me an email and I can tell you about some folks doing this.
Thank you.
Hey.
That Cheetah like hurdle environment would be a good idea for like the caution stuff. Randomly sized hurdles.
Could be, yeah. I guess the Cheetah does work decently well with model-based RL, so that could be a good choice.
Okay. And do you know if like other papers like comparing with that environment, or is that like implemented specifically for the Eisenbach paper?
I'm thinking. I'm not sure who else tried it. There was sort of a different but similar looking task in Chelsea and Justin's semi-supervised reinforcement learning paper, where they had the cheetah jumping over one hurdle of varying heights.
I see.
And there they were just studying generalization. They were trying to see if they could generalize to like larger heights than we trained on.
Yeah. I guess
I can't think of any others. Maybe check out the self-consistent trajectory autoencoder paper by JD and Abhishek.
Wait, can you repeat that?
Self-consistent trajectory autoencoder.
Okay.
They had some hierarchical tasks. I'm not sure whether they had the hurdles one, but they might have.
Trajectory.
Mm-hmm.
Okay, yeah, because I guess I mean like the equilibrium thing's done, but it'd be a good idea to just have like more environments
Mhm.
still in the things.
Yeah.
And it should probably work with like mole and gerbil and like other model-based stuff.
I think so, yeah. I mean, the cheetah tasks are pretty easy usually, so I think they should work well for model-based RL.
Yeah.
You can always just test it out first in just like one single environment to see if it works, but I think it should, yeah.
Okay, cool. Thanks.
All right, let's continue. So in the second portion of today's lecture, what we're going to talk about are some of the challenges in deep reinforcement learning. And this is really meant to kind of get you guys thinking first, for your final project, and also more generally, if you're interested in doing research in this area, what might be some open challenges that are worth thinking about. So what's the problem? Well, there are a number of problems. First, there are some challenges with core algorithms. So we can group these into three categories. One is stability. Does your algorithm converge? Does it do what it's supposed to? The second one is efficiency. How long does it take to converge? How many samples and how much wall clock time? And the third is generalization. So after your algorithm converges, does it generalize in a meaningful way? So in supervised learning, we've gotten pretty good at studying generalization. In reinforcement learning, this is something that's still in its infancy. But these are challenges with core algorithms. I think there are also some challenges with the assumptions. So reinforcement learning provides us with a very kind of clear, very well-defined problem statement, but we might still ask, is it the right problem statement? For a particular range of applications, for a particular range of real problems that you care about, is it actually the right problem formulation? What is the source of supervision in reinforcement learning? So where does the knowledge actually come from? So in supervised learning, it's very obvious. It comes from labels. In reinforcement learning, it comes from some combination of your environment and your reward function. So are there better ways for us to think about that? So I'll try to discuss each of these somewhat briefly, but hopefully give you some idea of what's going on in each category. So let's talk about stability. Some of you might have already figured out from doing your homeworks that reinforcement learning algorithms are a little harder to deal with than supervised learning algorithms. And there's probably more that we could do to improve this situation. So devising stable RL algorithms is quite difficult. And each category of RL algorithms has its own challenges in this regard. So for Q-learning or value function estimation methods, you have some issues like, for example, fit-to-Q or fit-to-value iteration methods actually are not contraction operators, and hence they don't have a guarantee of convergence. So most of the methods that we actually use in this area are not guaranteed to converge under the kind of conditions that we use them in, which are function approximation. So this is, to jog your memory a little bit, this was that whole discussion at the end of the first Q-learning lecture about how if you do the Bellman backup, that's a contraction in the infinity norm. If you then do a function approximation, that's a projection on the L2 norm, and together these two things end up with something that is not a contraction under any norm. And then there are a lot of parameters that you can vary to try to improve stability in practice, like messing with the target network delay, the replay buffer size, whether you clip your gradients, etc. And all these things end up mattering a lot to get good performance, in part because they mitigate some of the non-convergence issues. Policy gradient methods, reinforced natural gradient, etc., potentially don't suffer from these issues, but suffer from all sorts of other issues. So with policy gradients, you have a very high variance gradient estimator. So in practice, you do a lot of things to try to reduce the variance of that estimator. And most of those things also introduce additional hyperparameters. So you have lots of samples, complex baselines, etc. Your parameters are things like batch size, learning rate, the design of your baseline. And of course, these days, if you're actually using a policy gradient method, chances are that what you're really doing is you're using some kind of actor-critic style method. So you might have a policy gradient, but you might not have a full Monte Carlo policy gradient because the variance of that is too large. Instead, you use a critic. That critic is probably a bootstrap critic, which means that it suffers from all the issues in the previous category as well. And that's kind of bad news. Again, it might work well in practice, but it exposes a large number of hyperparameters and is a little bit unpredictable. Model-based RL algorithms, in some ways they're maybe a little bit better because training the model is a supervised learning procedure. But you have to choose the model class, you have to choose how you fit your model. And of course, optimizing your policy with respect to that model is itself very non-trivial. It either uses really complex kind of backpropagation through time methods, which suffer from vanishing or exploding gradients, or it uses a model-free algorithm to actually do policy learning under your model, which inherits all the issues from the methods up above. And the additional challenge with model-based RL, of course, is that getting a better model doesn't necessarily result in a better policy. So the loss that is being optimized when you train your model is not the performance of the resulting policy, it's the accuracy of the model, and those two are not the same thing. So you get some more subtle issues, like when you train your policy, you can exploit the model. If your model makes some mistake that is a little optimistic, then your policy will go and exploit that. So you have all these issues, and we can start thinking about ways to try to tackle them. But this issue with hyperparameters actually does pose significant obstacles to real-world adoption of reinforcement learning methods. So in simulation for your homework, you can try 20 different hyperparameter settings and see what works well. But if you're actually doing reinforcement learning in real-world settings, you can still do that. But then, of course, the cost of your algorithm is substantially larger. So if you have a real-world setting, you could tune your hyperparameters in your simulator, but it's usually not very representative. Or you can tune them directly on your task, but then your actual sample complexity is the time to run the algorithm times the number of times you need to run it to find the right hyperparameters. And that can be a much larger number. So in effect, it's kind of a stochastic search coupled with gradient-based optimization. So you can think about whether we can develop more stable algorithms that are less sensitive to hyperparameters. You can think about algorithms with favorable improvement and convergence properties. And there has been quite a bit of research in this area, but to date, no sort of single good solution. If you want a few examples of pointers, there's some discussion of kind of guaranteed improvement under assumptions that probably don't hold in the real world, but are at least a starting point in the original trust region policy optimization paper. There are some methods that have looked at safe or high confidence policy improvement methods, so where you can actually provide statistical guarantees that with a certain number of samples, you will improve your policy with a probability that's bounded below by some number. The problem with those methods is that, to date at least, they typically require very, very large numbers of samples to get those guarantees. But again, it can be a starting point. And also methods that adaptively adjust their parameters. So you could imagine, for example, methods that adaptively adjust how much they use a critic as a baseline based on how well that critic correlates with the real values. And people have explored this a little bit, but I think there's a lot more to be done there. OK, so that's hyperparameters and stability. Research-wise, it's sort of not a great topic for beating benchmarks because, for better or worse, the protocol that people use in reinforcement learning for benchmark tasks is to tune the hyperparameters on that task. That's probably not a very good thing, but that's what everybody does. However, it's likely a direction of research that's essential to actually make reinforcement learning a viable tool, because while tuning hyperparameters on benchmarks is nice for writing papers, it's not actually very nice for getting algorithms that are usable. So if this is a topic that sort of appeals to you, it's something where I think you can likely make a lot of impact. Let's talk about sample complexity next. So first, let me tell you a little bit about how the sample complexity of different methods compares to one another. So we can put these methods on a kind of hierarchy, where at the top of the hierarchy are gradient-free methods. We didn't talk about these methods a lot, but these are basically methods for doing policy search that don't use any gradients whatsoever. Things like covariance matrix adaptation, natural evolution strategies, and so on. Then we can, next we can have fully online policy gradient or actor critic style methods like A3C. Then we could have policy gradient methods that are batch mode like TRPO. And then we can have replay buffer value estimation methods. So these are now getting to be off-policy algorithms. Algorithms like Q-learning, DDPG, NAF, SAC, et cetera. Things that use a replay buffer and data from previous iterations. Then model-based deep RL methods. And then shallow model-based deep RL methods. So these are model-based methods that use typically non-parametric function approximators like Gaussian processes. And I wrote these like this in a column because every step down this way incurs a sample complexity improvement of about 10x. So this is sort of back of the envelope calculation by cobbling together a bunch of numbers from different papers, with the caveat that some of the tasks are in subtle ways a little bit different. But if you look at, for example, Salimans et al. Evolution strategies for RL, they test on a task, on the half-cheetah task. If you look in a paper that uses A3C, you can see what it takes for them to do the half-cheetah task. So you end up with, that's for TRPO, you end up with about 15 days of real time for this one. For the Salimans et al., it's about 10x that. So 10x improvement from essentially starting to use gradients. From starting to use batch mode policy gradient, you can look up performance of TRPO with GAE. It's about 1.5 days of real time. And cheetah is a very simple task, so this 1.5 days would become a much larger number for more complex tasks. So you get another 10x improvement from doing batch mode policy gradient. And then if you switch to off-policy algorithms, then you get about 3 hours of real time. When I say real time, I mean this is like if the cheetah was actually running in real time. Of course, your simulator runs faster. It takes about 3 hours with, this is from the QProp paper, but it's about the same for DDPG and others. And it turns out that if you do some of this stuff on, in the real world, this is NAF running on a real robot, it takes about the same amount of time for simple tasks. So 2.5 hours here, 3 hours, so somewhere in that ballpark. Model-based RL, this is half cheetah for model-based RL, about the equivalent of 5 minutes of real time. And this is guided policy search. So again, about a 10x improvement here. And then for shallow RL, it's a little hard to compare because things like Gaussian processes are very difficult to use on tasks like half cheetah, but for simpler tasks like pendulum and so on, there you can compare, and again, you get another factor of 10 improvement. So you go from things that take minutes over here to things that take days or, you know, in the case of gradient-free methods, months up there. Now, from looking at this picture, you might think, well, why the hell would anybody ever do, like, you know, A3C or TRPO if they're so much slower? In practice, if you have a very fast simulator, the actual wall clock time, the actual amount of time you have to wait, tends to actually be backwards. So the model-based methods are computationally quite a bit more expensive. In a sense, when you're doing something like a batch mode policy gradient algorithm like TRPO, you're kind of trading off simulator time for learning time. So you use more data, but you do less compute per data point. So in terms of how long you actually have to wait, if you have a very fast simulator like Mujoko or the Atari emulator, it might actually take you less time to do something up here. If you have a lot of parallelism, if you can use an entire data center to do parallel computation, then actually these gradient-free methods like natural evolutionary strategies might be the fastest of all because they can be parallelized most efficiently. But in terms of number of samples, then things like model-based RL or off-policy model-free RL are a lot more efficient. And the differences are drastic, you know, so it goes by factors of 10, potentially. So that's the story with sample complexity. And of course, poor sample complexity is an issue for a whole range of reasons. You need to wait for a long time for your homework to finish, which means that you might not submit on time if your deadline is 11:59 p.m. But that's a, you know, sort of a very, you know, a problem that's very specific to this class. Outside of this class, real-world learning becomes difficult or even impractical if you have very high sample complexity. So there are just some things that you cannot do if you need your system to collect, you know, months or years of experience. It also precludes the use of expensive or high-fidelity simulators. So maybe you do want to learn in simulation, but you have some really sophisticated simulator with like finite element analysis for your complicated, you know, aircraft and so on. Maybe it's just difficult to use that simulator with a very inefficient algorithm. And it greatly limits applicability to real-world problems. So there's a lot more that can be done here. You can think about better model-based RL algorithms, maybe relaxing some of the assumptions that make those methods difficult to apply in certain problem settings. Design of faster and more efficient algorithms. You know, methods that, for example, introduce effective but somewhat you know, incremental tricks to accelerate existing RL algorithms can actually have a lot of value if it makes the difference between making the method so inefficient as to be inapplicable to the real world versus efficient enough to actually be usable. And then for sort of more speculative, more complex solutions, you can also imagine methods that reuse prior knowledge to accelerate reinforcement learning. So beyond just designing more efficient core algorithms, you can think of algorithms that get a little more creative, that use data from previous tasks or from, you know, other related domains to learn more efficiently. And that's what we learned about when we talked about meta learning and multitask learning. All right. Last core algorithm challenge, scaling and generalization. So if you work on supervised machine learning topics like computer vision, typically you deal with problems that are large scale, that emphasize diversity, and that evaluate on generalization. In reinforcement learning, this is typically not the case. So reinforcement learning tasks that you would typically work with if you're sort of doing research in this area are small-scale tasks that emphasize mastery, meaning that they emphasize how well can you do at the task at the end, what is your final reward, as opposed to evaluating on generalization. And it's actually very difficult to study generalization with tasks of this sort because they don't have a prescribed test set, but they also don't have the kind of diversity that you need to actually get meaningful generalization. So you can't really hope to get a policy that makes the ant run really fast to generalize to making the ant jump or run over an obstacle course because the training environment is not diverse enough to accommodate that. And when it comes to studying generalization in diverse environments, reinforcement learning actually has a pretty big problem. It's pretty easy to study generalization in supervised machine learning because in supervised machine learning, somebody went out and collected a data set, maybe ImageNet, and they did this once. And once they've collected this data set, you can use it as many times as you want. And then once you're happy with the model that you have, you can deploy that model to your system, and you don't need to recollect the data. In reinforcement learning, of course, you recollect the data as you train your model, which means that every time you modify something about your method, you need to do this all over again. So this is done many, many times. And of course, actual reinforcement learning is much worse than that. Actual reinforcement learning also has an outer loop and that outer loop is you. So every time you change something about your algorithm, of course, all this has to be done all over again. And that makes the experimental cycle very onerous if what you're dealing with is a task that emphasizes diversity and generalization. If in the inner loop of this thing, you have to collect sort of an ImageNet-sized data set that will result in, ImageNet level generalization. And because of that, a lot of people don't study generalization in reinforcement learning. So one of the things that you could think about is that, well, first of all, is the situation bad? Yes, it's bad. So here's a video of TRPO learning to run with a little humanoid. At first it falls many, many times, and then it starts running pretty effectively. A few observations about this. It's pretty cool. At least I think it's pretty cool. It takes about 6 days of real time if this was an actual robot. But the problem is that in those 6 days, it learns to run on an infinitely large flat plane. If it was running on like roads and gravel and doing parkour and whatever this is, like if it was doing all these different things, the training process would actually amount to going round robin through each of these different environments for every single iteration, and then in the outer loop having 2,000 plus iterations of that. Now that's something that you would never actually be able to do with anything resembling real data. In fact, you'd be hard-pressed to even do this in simulation. So maybe if we really want to study generalization in a meaningful way, we need to start thinking more seriously about things like off-policy reinforcement learning, where you can use large data sets, but you don't have to recollect those large data sets every time. So it's kind of a different view of off-policy reinforcement learning. It's not just reusing data from past iterations, but it's actually bootstrapping off-policy reinforcement learning with a large prior data set. And that could then allow you to do things like adjust your model, change your algorithm, without having to recollect all of your data. So maybe something to think about when it comes to generalization RL. And of course, this stuff is not just for robots. If you think about the kind of domains where somebody might want to use reinforcement learning in practice, very, very often these are domains that are characterized by situations where it's very difficult to run on-policy data collection and where there are existing data sets. So in autonomous driving, lots of prior data, but running a car with a partially trained RL policy is a very dangerous thing. If you imagine language and dialogue, these are things that need to be learned from actually interacting with human beings. So having your agent explore by actually interacting with lots of human beings might be expensive, but there's lots and lots of logged data that can teach you about what language and dialogue looks like. Same thing in finance. Actually trading stocks might be a little bit risky, but there's a lot of historical data available for that. All right. Now, let's briefly discuss some of the assumptions. So far I talked about challenges with core algorithms. I want to also talk a little bit about some of the challenges with the assumptions. So we might imagine whether that perhaps if we have realistic reinforcement learning settings, we might really want to have a multitask formulation. And a lot of the things that I mentioned so far might kind of get you thinking about that. If you have a multitask formulation, you can actually start thinking about generalization in a meaningful way. You can start thinking about models that can be effective in diverse real-world environments. And of course, we know that in a multitask setting, you can embed multitask problems into single-task RL. So you can imagine that you basically have a stochastic MDP where in the first time step there's a choice that's made about which domain you're placed in, and then you can use your standard RL methods to tackle multitask problems. But maybe it doesn't require new assumptions, but perhaps you can get better algorithms by making use of the fact that this is a multitask environment. Maybe you can get better optimization methods from studying the particular properties of multitask RL settings. Generalization from multitask learning. So, of course, if you want to study generalization, it makes a lot of sense to look at how training on multiple tasks can allow you to succeed at new tasks. And we've covered a few topics that get at that, like policy distillation. We talked about some algorithms for this, like actor-mimic. We talked about meta-learning algorithms that also get at a variant of this point, and many others. You can also think about unsupervised or weakly supervised learning of diverse behaviors. This is actually quite related to what we talked about in today's lecture. Can you acquire useful knowledge from interacting with the world without very rigid supervision like reward function, and use that to generalize or to acquire new skills more efficiently? So there are a few pointers to related work here. But more generally, it helps to think about where the supervision for your reinforcement learning procedure is going to come from. So if you want to learn many different tasks and then generalize, you need to get those tasks from somewhere, and that's either going to come from somebody working really hard to define all those tasks via reward functions, or it's going to come from some kind of cleverness involving learning objectives or rewards, perhaps from demonstrations, perhaps from watching humans, or perhaps from unsupervised learning procedures. And these are all things that I think are worth thinking about. So perhaps you could either harvest your objectives from watching other agents, or you generate your objectives automatically, use that to get many different tasks, and then get generalization from those many different tasks. And you might also get to thinking along these lines and think about, well, what is the role of the reward function really? And in many ways, the way that we do reinforcement learning today somewhat abuses this notion. So, as I mentioned in the beginning of this course, you could think at first that you could get a little character like this to walk forward by defining a reward that just says, you get a 1 if you walk and a 0 otherwise. But in practice, we don't really do that. We define some pretty complicated reward, more or less to address the challenges of optimization. The fact that reinforcement learning with very simplistic rewards like this is just difficult from an exploration and optimization standpoint. So we're doing something when we define these more complex reward functions. We're essentially providing more supervision. We're providing more knowledge to the method. And we know for humans and animals that the structures in our brains that at least we believe right now to be responsible for reward are not simple. They're not just things that sort of give you a +1 if you if you like just ate a delicious meal or something. There's a lot of sophistication there, and so the current hypothesis that the basal ganglia is largely responsible for that. And it's easy to imagine why that sophistication needs to be present in there. If you imagine that you're the cheetah chasing the gazelle out in the savannah, if you only got your reward when you actually successfully chased down that gazelle, you'd essentially have to bank on running around randomly until a gazelle randomly lands in your mouth, and then you get that high reward. That's very unlikely to happen because the gazelle has its own desires and its own reward function. So it's clear that there's quite a bit of sophistication and supervision that's coming from this thing, and it's something that we don't think about very hard when we're just designing RL algorithms. We could imagine unsupervised reinforcement learning algorithms that interact with the world without a reward function to learn some kind of prior to then help ground specific skills. You can learn something about the world like a model or like some of the skills that I discussed in today's lecture, and maybe use that to learn to quickly solve new tasks. Or you could acquire reward functions from other sources. What are some other sources of supervision that you can think about? Well, you could think about demonstrations, so watching people, maybe people demonstrating skills like we talked about in the advanced imitation learning lecture. You can think about language, maybe from looking at the structure of how people describe scenes, you can figure out something about what kinds of behaviors are useful or interesting, or how those behaviors should be performed. You can think about human preferences, maybe other kind of secondary sources of supervision that are not as detailed as demonstrations, but where you can basically ask people, is this better than this other thing? And maybe you get much more fine-grained knowledge than you would from just a 0-1 reward function. And of course, there's sort of a more philosophical or conceptual question, which is, should we rely on supervision to tell us what to do or how to do it, or maybe a little bit of both? In principle, kind of the classic RL picture says the reward tells you what to do, the algorithm tells you how to do it. But of course, when we look at reward functions of this form, it's pretty clear that that's not actually what's going on in practice. All right. So that's maybe the more, I'll skip this part. That's maybe the more practical aspect of this discussion. But I do want to briefly, in the last few moments, come back to kind of the bigger picture with RL. So if you remember, in the very first lecture, I talked about how we could imagine that perhaps learning can be the basis of intelligence. And if we subscribe to that notion, then it leads to the conclusion that we need learning algorithms that can reason about decision-making and control and can represent complex sensory modalities. And from that, we might arrive at the notion that reinforcement learning is what will allow us to reason about decision-making, deep models which will allow us to reason about complex input-output mappings. So therefore, maybe if we study deep RL, we'll get a little bit closer to reinforcement learning algorithms that can solve complex problems end-to-end and represent something that resembles intelligence. But of course, there's clearly something missing since we're not there yet. And we might ask, well, what is the thing that's missing? And this is a slide that I borrowed from Jan LeCun that describes his hypothesis about what's missing. And I think it's one hypothesis of many. And in the next slide, I'll tell you how I think it's one hypothesis of 3. But first, I'll summarize what his hypothesis is. His hypothesis is basically kind of an information theoretic hypothesis. It says, how much information do you get from the supervision that you're receiving about the world? If you have a supervised learning algorithm like ImageNet classification, well, if you have, let's say, 1,000 classes, you're getting roughly 10 bits of supervision per image. So if you need a certain number of bits to get a degree of intelligence, then you take 10, you take that number, divide by 10, and that's how many images you need to see. If you're doing unsupervised learning, or if you're predicting the future, then you're predicting a very large number of bits. Maybe you're predicting the next image that you'll see. Now, if you have many more bits of supervision per data point, then correspondingly you might need many fewer data points to get the same number of total bits of supervision. So then the next thing he says is that if you're doing reinforcement learning, well, then you're actually getting a comparatively smaller number of bits of supervision. If you have fairly simple reward functions like, did you win the game or not, you're getting just a few bits, not per image, but at this point per trial. So now you might need a very large number of trials to get the same number of bits of knowledge about the world if that knowledge is really coming from the reward function. Okay, so maybe some food for thought. Some cake, yeah. So where does the signal actually come from? And I think this is one hypothesis. There are other hypotheses too. So one hypothesis, which I'll nickname Jan LeCun's cake, is that, well, maybe this notion of learning from rewards is not going to be good enough, and maybe we need sort of more calorie-rich sources of supervision. So maybe things like unsupervised or self-supervised learning can provide those bits of supervision that we need to acquire useful representations, maybe something like model learning, predicting the future, and then on top of these, we can acquire the skills that we need from those relatively uninformative reward functions. So this view says that, well, to really get to the heart of the matter, you need to couple reinforcement learning with very sort of high bandwidth unsupervised or predictive learning methods. And this is nice because it gives you a lot to do before you even accomplish your goals. So maybe that cheetah, even before it's caught its first gazelle, is going to learn good visual features of the world by learning to predict what's going on around it. There is another hypothesis you can imagine. Well, maybe the other hypothesis is that the additional supervision comes from the fact that you don't just learn from a reward function, but you also learn in a somewhat cooperative world where you have other agents that will help you along. If you're growing up, hopefully you have the rest of society and your parents and so on to guide you. Maybe for your agents, you have some imitation learning and some kind of cooperative learning environment to help them along. Humans, and in fact many animals that we would consider to be more intelligent, are actually social animals. And humans have culture, and maybe that's for a reason. Maybe that's actually a big part of the mechanism that allows intelligence to arise, even in situations where otherwise supervision might be very scarce. And then there's another view, which is, you might kind of call it the RL purist view, which is that actually all this stuff about reinforcement learning having too little supervision is nonsense. Because even though the reward function might be relatively uninformative, your agent is not learning from the reward function. It's learning from the reward together with its interaction with the world. And maybe when you back up that reward via the Bellman backup into a value function, relatively simple rewards give rise to very complex value functions. And that actually contains a lot of information, not just about your goal, but also about how the dynamics of the environment influence your goal. And perhaps all it really takes is just a little bit of learning signal propagated through the environment dynamics to give you a very rich source of supervision that entangles the dynamics of the world with your reward function. I don't know which one of these is true, but I think they're all worth thinking about. And it may be some combination of all of the above. So maybe the real question is how we should go about answering these questions. And I think one very important part of this is to pick the right problems. So it's very easy to jump to working on benchmark problems where you can try to get better numbers. But remember that if what you're really after is to understand machine intelligence and maybe human intelligence a little bit better, you need problems that reflect the challenges that you actually want to tackle. Maybe problems that are more realistic, more diverse, capture more of the variability in the world, or more of the challenges that you might encounter in real-world settings. Pay attention to other parts of machine learning, like generative models, prediction, etc., not just RL algorithms, because it may be that important parts of the puzzle might come from those fields as well. And carefully understand the relationship between RL and other fields, because it's likely that some degree of rethinking the problem formulation or incorporating ideas like unsupervised learning, prediction, and imitation will be important to arrive at substantially better solutions. All right, well, that's it for today's lecture. I'll see you all on Wednesday for Ophir's guest lecture, and I encourage those of you watching online to come to class for those guest lectures. So yeah, see you all on Wednesday. Oh, and I'm going to have my office hours for the next 30 minutes right outside this room because I couldn't book a room in Soda.